Hi, and welcome back to another video. It's a somewhat tutor, and in this session we're going to be looking at how to use the method of joints to find member forces. So in this example we've got a rigid truss with two supports, a pin support at point A and a roller support at point E. We've also got one external force of magnitude P, and that's located at node B. So what do we need to do to find the forces inside these members? Well, first of all, we always need to determine what are the reaction forces from these roller supports and the pin support. As usual, we're going to use the equations of equilibrium, so that's going to be the forces in the x and y direction and the moments equaling to 0. I've got my key as usual on the right hand side, so positive going to the right, positive going up, and clockwise moments as going positive. So let's begin with a free body diagram to find out what we have at points A and E. So again, with a free body diagram, we're just going to draw the general shape. We're going to label what we have. So we've got a pin support at point A. Again, using the key, we've got a resultant vertical force and a horizontal force. So we're going to label that VA and HA. We've got a vertical reaction force VE, and we've got an external force of P. Again, there's nothing else that we can get from this example. So what do we need to do? We need to use the three equations, which is the sum of forces, I'm going to say going up as positive, is equal to 0. The sum of forces going to the right as positive is equal to 0. And the summation of moments going clockwise about a point is equal to 0. Again, this is the same as if you're going to label this y, x, and then you've got your moment. So let's begin with the summation of forces going up as positive. Again, these equations are going to allow us to work out the unknowns in HA, VA, and VE. So what do we have? We've got VA, which is going up, plus VE is equal to nothing, so it's equal to 0. We've got nothing else going down and nothing else in here. We've got two unknowns in one equation, so we can't really do much. Therefore, we need to use another equation. So let's look at the horizontal forces. So we've got positive HA plus P is equal to 0. Therefore, we can say HA is equal to negative P. Let's look at the summation of moments. Now we need to pick a point. In this case, as we've got unknowns in VA and VE, it's good to pick one of those, as the perpendicular distance will be 0. And in the case of point A, we've got two forces, so it'll be easier just to use that point A. So we know HA and VA will cancel through, as the perpendicular distance is 0. That's going to leave us with two forces, VE and point P. Since we're taking moments about point A, we know that force P goes to the right of node B, point A is directly down, so that's to the right, directly down, and if you imagine we're completing this, that's going to be back around, and that loop is clockwise, so that's going to be a positive moment. So we've got P, which is the force, the distance, perpendicular distance between B and A, which we've got in the example, that's A. We've got a vertical force at point E, which is going to be directly up, and point A is directly to the left. So if we complete the loop, that's going to be back down to the right. We follow the arrows, that's going to be counterclockwise, so that's a negative. So that's minus VE, and the distance is, well, B to C is 1A, and therefore C to D is also going to be an A, so that's A plus A, which is 2A, is equal to 0. Therefore, if we rearrange to get VE as a subject of the equation, we can say that VE multiplied by 2A is equal to PA. Cancel through the A's as they're both in common, and divided by 2. Therefore, VE is equal to P over 2. And what we can do now is substitute VE back into this equation to get VA. We can say VA is equal to negative VE, so taking V across to the other side. This should be all capitals. Therefore, VA is equal to negative P over 2. So what I'm going to do is just draw a little quick table so we can write what we have. So we've got HA, VA and VE. So we've got VA is equal to negative P over 2. We've got VE as positive P over 2. And we've got HA as negative P. So that's our support reactions. And what we need to do is now look at the internal forces. So what I'm going to do now is just clean up the screen so we can still visualize and look at the diagram whilst we have it on the screen. So what does the method of joints entail? Essentially what we need to do is start at a certain point and we need to take cuts at all the members that are linked to that point. And in doing so we need to make some assumptions. We're going to assume that all those cuts that we've taken have tensile forces. And once we use the equations of equilibrium to find the unknowns, we can start using those unknowns which we've just worked out and start moving around this truss. But it's going to be a really good idea to use a position that we have the least amount of members, but also a member that we have already existing information. So if we look in this example, we've just worked out the resultant forces from this principle at A, but also at E. We've got information also at B. So those three, we have some information. But if we look at these points and say which members have the least, or so which point had the least members, well, point B has 3 members, going down to A, going diagonally to F, and going to the right of C. So that's 3 members. E and A have 2 members each. So it's going to be a really good idea to use either A or E first. But in this case, let's just go with A. So what we need to do is take cuts. Essentially what we're going to do is take cuts at all the points. Let's just say here for member AB and here for AF. And then what we need to do is draw a free body diagram at joint A. So if we look at joint A, if we take cuts, the free body diagram is going to look something like this. So we've got tension between AB. Again, it's going away from the point. So in tension between 2 nodes, the forces always point towards each other, and in compression between 2 nodes, the forces always point away from each other. So as I said, we're going to assume it's in tension. So we've got 2, which is TAB and then also TAF. We've got VA as negative P over 2, and that negative means we've assumed it was going up in the positive direction. In reality, that's actually going down as P over 2. And then we've also got HA as negative P. Again, that means our assumption of the arrow going to the right was actually wrong. So we're going to say it's positive to the left. In this case, positive P going left. So again, we're just going to use the equations of equilibrium to work through AB and AF. So if we look at this, we've only got one reaction force, both going in the horizontal direction and in the vertical direction. So we can say that summation of forces going up is equal to 0. Therefore, we've got TAB minus P over 2, as it's going down is negative in this case, is equal to 0. Therefore, TAB is equal to P over 2. Now we can say summation of forces going to the right is equal to 0. Therefore, TAF minus P is equal to 0. Therefore, TAF is equal to positive P. So that's what we've got. I'm just going to add it to this table here. So we've got TAB is equal to P over 2, and we've got TAF as positive P. So what I'm going to do is just take a moment to clean the screen, Now, what we need to do, we can move on to the next member. In this case, I'm going to move on to member B. So we can either move on to member B or member F. But in this case, F is connected to pretty much all the points. We've got point E, point A, point C, point B, point D. So that's a lot of information that we don't know, and it's going to be best to move on to point B. In this case, we've worked out the force between A and B, so we need to take cuts at all the other members we don't know. So that's between B and C and B and F. So let's begin with joint B and draw the free body diagram. So that is going to look something like this. Again, BC is unknown, so we're going to assume it's tension, and that's BC. We know TAB because we've just worked it out. Again, it's positive, so that means our assumption in tension was correct, and we can say the arrow is going away, which is P over 2. We've got external force of P acting on node B, and now we've also got TBF, which is diagonally. Now, this diagonal force, what we need to do is resolve it to get the horizontal and vertical components. So what I'm going to do is just on the side here, draw that out, which is TBF, so it's a little bit more clear. We go to the right and down. And as we've got a square pretty much, because it's, if you look at the dimensions of this square, so that's A is the width and height as A, so that's A over A. We can say the diagonal length, which is A over A, and this angle we can work out as being, that's going to be opposite, that's going to be adjacent, so we can use tan of theta is equal to A over A. To get theta, that's going to be the inverse tan of 1, A over A is just 1, so theta equals 45. So that angle is going to be really important because we know that angle now is 45. And to get the horizontal and vertical components, that sign is going to be really important. So remember, if it's away from the angle, well, that's going to be also 45, as that's a right angle triangle. That is going to be cos, and that's going to be sine. So let's look at the summation of forces going towards the right, or going upwards at first. So we've got negative P over 2 because it's going down. We've also got a negative from this TBF, so that's negative TBF. We've worked out this angle to be 45, so therefore this component is going to be sine 45, and that's equal to 0 as there's nothing else acting on that point. So we can say therefore TBF sine 45, which is root 2 over 2, is equal to negative P over 2. We can cancel the 2's out on both sides. We can say therefore TBF is equal to negative P over root 2. Now we can eliminate the root 2 by timesing it by root 2 over root 2, but in this case I'm just going to leave it as it is. So that's TBF. And what we can do now is move on to look at the forces going to the right. So that should also equal 0. We've got a positive P. We've got this component going to the right, so that's positive TBF cos 45. We've also got TBC as going to the right, so that's positive TBC is equal to 0. Cos 45 and sine 45 are the same, so that's root 2 over 2, and we plug in TBF from here. So we've got P negative P over root 2, as TBF is negative. That's multiplied by cos 45, which is root 2 over 2, plus TBC is equal to 0. The root 2's will cancel through. That's P minus P over 2 plus TBC. So therefore we can say TBC, which is negative P over 2. So you've got p minus p over 2, which is positive p over 2. Take it to the other side, and we get negative. So what I'm going to do is just add it to this table here. So we've got t bf is equal to negative p over root 2, and we've got t bc as negative p over 2. What I'm going to do now is just take a moment to clear the screen. So let's move on to the next node. Now I'm going to look at node C. So node C, we've got a vertical node which is going straight to F, so that's unknown. So we're going to take a cut, but also we're going to take a cut at between C and D. So let's look at the free body diagram of joint C. So we've got a tension going from C to F. Again, that's unknown. We've got the tension between C and D, and that's unknown. And we've got TBC, which we've just worked out as being negative P over 2. So that's going to be pointing inwards as it's negative, so that means that our assumption going tensile is actually in compression. So that's P over 2. Again, now we're going to look at resolving the forces. So in this case, we can say the resultant force is going up as equaling 0, which is just TCF is equal to 0 because we've got nothing else working. So that middle node has got no force going towards internally. Now the summation of forces going to the right as being positive is equal to 0. So we can say TCD plus P over 2 is equal to 0. Therefore, TCD is equal to negative P over 2. So again, let's just add it to this table, which is T CF is equal to 0. What I'm going to do is just add it to the side here, which is T CD is equal to negative P over 2. Now I'm going to clear the screen and move on to the next joint. So let's move on to the next one. Let's go to F because we've worked out pretty much AF, BF and CF. So the only unknown ones are F and D, which is going to be the diagonal one, and F and E, which is here. So let's begin with the free body diagram. Always important to draw the free body diagram as that's going to expose all of the unknown forces. So we've got AF, which is going to the left. Well, let's look at our table. We've got positive P, so that's definitely going in tension. We've got CF, which is 0. We've got BF, which we worked out as negative, so that's coming inwards as P over root 2. We've got the tension, which we're going to assume as TFD, and we've also got TFE. So let's use the equations of equilibrium. We'd say the summation of forces going up as positive is equal to 0. Therefore, we're going to have 2, which is the resultant vertical vectors from these diagonal forces. So we've got down and to the right, as this is a downward force, and we've got to the right and up. As we know, we've worked out previously, the angles is 45, so that's going to be sine and cos 45 to use in resolving these forces. So in this case, let's look at BF. So we've got negative P over root 2. We know we're looking at, let's use this angle, we're going to look at this downward vertical, so that's going to be sine 45 as it's away from the angle, sine 45 plus TFD, again sine 45, which is equal to 0, so there's nothing else. If we swap it around, the sine 45s will cancel through, so therefore we can say that TFD is equal to positive P over root 2. That's F. Now if we look at the forces going to the right, is equal to 0, so we've got TFE, which is the bottom element here, plus TFD, and the horizontal component, which we've just worked out as P over root 2 times cos 45, which is, well, we already know as we root 2 over 2, so we just add that in straight away, root 2 over 2. And we've got the positive of this component bf, which is p over root 2, cos 45 again is root 2 over 2. And we've got the negative p from AF. So the root 2's will cancel through in the multiplication. So we've got TFE plus p over 2 plus p over 2 minus p. So we've got half a p plus half a p, which is a whole p, minus 1p. So TFE, we worked out, then is 0. So then let's add that to the table. So we've got TFD as p over root 2, and we've got TFE as 0. Now I'm just going to take a moment to clear the screen. Now let's look at the next member. So we've got E and D free, but let's just look at joint E. So they're both just going to be only one left, which is just a vertical member here. We can choose any, but as E's got the fewer members, it's going to be the easier to look at. Joint E. We're only interested in the vertical force. So again, we're going to take a cut. We've got tension between E and D, and we've got the vertical force, or VE, as positive P over 2 in our table. So that's P over 2. Intuitively, looking at that, the force is going up must equal 0. So therefore, TED plus P over 2 is equal to 0. And then we can take it to the other side. We can say TED is equal to negative P over 2. And we can add that to our table, which is TED is equal to negative P over 2. What I'm going to do is just quickly clear the screen, and I'm going to show you a diagram of what all the internal members look like. So here is a final diagram of all the internal forces within the members. Here the green represents tensile or tension, and the red represents incompression. What I've done on the diagram members is just cleaned up the root 2's at the bottom. And so if we go around between points A, B, C, D, E and F, what you see is the table should align with all this information here in the diagram. So this is how the diagram should look if we are looking at all the forces. So hopefully that's made a lot of sense. What I'll do is add a few more complex examples as we go down the line. If you've enjoyed the video, please give it a like. Please consider subscribing and helping me to 100 subscribers. And I'll see you guys in the next video.